managed to establish modulus of proofs that if I have a I'll have a irreducible admissible representation phi of SL2R if and only if the universal enveloping algebra acts irreducibly on the k finite vectors. Right? Whether you understand analytic vectors, smooth vectors, whatever else we did, this is what we have in hand. Okay, so I'll write down that first, and then we'll. Okay, so far we have. So let me write this as a theorem by the admissible summation of SL2R. Then P is irreducible. So this is irreducible for the G action, right? So for G, if and only if Vk, the k finite vectors, is irreducible for the universal enveloping algebra, right? So this is where we are. Okay, so now we move towards classification. So we have a list. Remember that we have a list of unitary irreducible representations, right? The two sets of principal series, two sets of discrete series, and the complementary series, right? And trivial representation. Okay. So we'll start with the following. So let me quickly write down. So G is the algebra, SL2R, and GC is the complexification. So this is SL2C, and we choose a basis for SL2C. I'll need the expressions. Well, the matrix expressions are not needed. The bracket relations are what is more important. But let me write down H bar. So this is different from the X we have been using before or in other lectures. So this is 0 minus I 0. Then I have X alpha half 1 I. Don't bother about the half 1 minus 1 and X minus alpha. So that is half 1 minus I minus 1. Okay. And the bracket relations is H bar X alpha is 2X alpha and H bar X minus alpha equal to minus 2X minus alpha, and if you take the bracket of X alpha, so you have seen this in many forms by now. This is H bar. Okay. So those are the root vectors with respect to the action of this element H, and this element H is what generates the compact group. So note that as well. So note that ITH bar. So this is something which we have seen earlier. That is 0 minus t 0. So that if I exponentiate this, I'm going to get the compact group, right? So exponential ITH bar is cos t minus sin t cos t. So in other words, the algebra of K is simply IT H bar T, right? So we can write it like that. Sorry?
0 t minus is
Yeah. Let's not bother too much about all the plus minuses. So where are we? So if I take so now we want to restrict ourselves to unitary irreducible ones. Okay, even though whatever I say is true for admissible irreducible, which can be seen, but our aim is to classify all the unitary irreducible representations, and remember that we have that list, right? So let phi v be irreducible unitary representation of R. And well, yeah, I should have said that. So we have the representation of phi dot representation of the universal helping algebra. So pi acts irreducibly on V, so pi dot acts irreducibly on. So that's irreducibly on V. Okay. Yes. Right. So there are a couple of things which we know already. I'll write it down just to set the stage for the classification. So what all do we know on Vk? So this is the k finite vector. So this is direct sum Vn and Z is irreducible for UGC. Okay. Vk is k stable, meaning k invariant. K is the compact group, right? That is because this is simply the direct sum of Vn's. And if I take a vector from here, apply k, I'm going to land there. There is no need of a closure and things like that. Okay, so that means under k action, right? So under the k action, and the k action decomposes exactly like what is written in the first thing. Dimension Vn is 0 or 1, right? We proved this as well. So, because we are starting from a representation of G, the action of the Lie algebra of K and the action of the group K are compatible. The action of K, so this is the Lie algebra of K on Vk is the infinitesimal form of the K action. So this is the compatibility we have seen in Illich's lectures. K action on V. And the last one was that Casimir acts like a scalar, right? Casimir acts as a scalar because of irreducibility. Right, so we have done all this. Okay? So when one studies GK modules, we have these conditions, perhaps not this one. But here everything is fine because we are starting from a representation of the group. Okay, so all this we already have. Okay, so we are trying to move towards classification. So first we will do the infinitesimal one. Classification. So that means the classification, the Vk, the k finite is. So we have certain data here. The data is the k types that are appearing in the decomposition, and the Casimir acts like a scalar. Okay, so that scalar we will call Q. Okay, so Q is some number plus the k types. So the ends that will appear. Okay. So let's start with the easy lemma. So a vector V is in Vn. So Vn, remember, is the nth K type. If and only if. Okay, I'm going to drop pi dot. Okay, so when I say h dot V equal to nV, so h dot V or hv is pi dot of h acting on V, right? H is not h bar. Right, h bar is the element from the Lie algebra. Right, we started with that. So the pi dot will be dropped from now onwards. Okay. So this is just the Lie algebra action via the representation. If and only if h bar V equal to nV, that is trivial, right? So V is in Vn. I know that pi of exponential I th bar, right? Where is that? Okay. So exponential I th bar is in k, and so it will be e to the I t times v, and when I differentiate, I'm going to get. And conversely, if this is true, then I need to compute exponential I th bar acting on v, but h bar v is n v, so you expand it, you will get e to the I n. Right? So that is a trivial. Second one is more important, but it's easy, and we have already seen that in the last lecture. Pi dot of x alpha maps Vn to Vn plus 2, and pi dot of x minus alpha maps Vn to Vn minus 2. Okay. So yeah, okay. This time I have written pi dot. But so x alpha maps Vn to Vn plus 2, and x minus alpha so reduces the weight. So this follows from the commutation relations, right? So let's do one of that. Then we'll see. So proof. So let me keep writing pi dot for the time being. So pi dot x bar, pi dot x alpha v equal to, well, you do the usual thing. Pi dot of x alpha, pi dot of x bar v plus pi dot of bracket x bar x alpha acting on v, and this is so this. And also v, I'm starting with v in Vn, right? And I want to say that x alpha maps Vn to Vn plus 2, right? So this is just n times v, right? From the first one. And here, this bracket, x bar bracket x alpha is 2x alpha. So this is just pi dot of x alpha to v, right? So I'll get n plus 2. So n plus 2 times pi dot of x alpha v, right? So this tells me that pi dot of x alpha v is in Vn plus 2, right? So this is easy. This is, you have seen in the case of Faraday as well. Vn plus 2. Similarly, x minus alpha will bring in a minus 2, and then you have it. Okay, so this, even though it's a simple proposition, it has important consequences, and from now onwards, it's the arguments are simple because we have already done the hard work. We just need to analyze what are the K types that can appear. Okay, so I'll write down one more fact: the Casimir. Casimir omega takes the form, so you can use these basis elements to write down the Casimir, and we'll get x bar square plus 2x alpha x minus alpha plus 2x minus alpha x alpha. Okay, just like the e plus e minus, it's the same. Okay, so to analyze all the K types and so on, we'll need one more computation, which is what will allow us to conclude what are the K types that can appear. So we'll see that, well, you have already seen that the eigenvalues jump by 2, right? So from Vn you go to Vn plus 2. So we write it as a proposition. This can stay there. So now we'll drop the pi dot. Okay. Let V belongs to Vn, L is greater than 1 some integer. Then, so I'm going to write down some formulas. We'll prove one of them. Then x alpha, x minus alpha L. So L is an integer and that is just the power. So this x alpha means pi dot of x alpha. Okay, we are dropping pi dot now. Acting on V, V is a vector from V and the nth K type. So this is, so we find the expression 1 by 4. Q, remember Q, not from the James Bond movie. This is the scalar with respect to the Casimir's eigenvalue. Q minus, well, some slightly complicated expression, n minus 2l. So n is the Vn's n, L is the power of x minus alpha, times n minus 12 plus 2 times, okay, so I should have been careful. Okay, x minus alpha to the L minus 1 V. I hope this is visible. And similarly, if I have the other order, that is x minus alpha and x alpha to the L, I have a similar expression. Okay, so let me just write it down that as well. So x alpha to the L, V still comes down. Okay, 1 by 4 Q minus this expression changes slightly, n plus 2L, n plus 2L plus 2 times x alpha L minus 1 V. So I want to keep that because this is something we will use. So those expressions are sort of important. So I'll keep that upstairs. Okay. Well, proof is easy, but let's stare at the expression for a while. So the x alpha, so remember that x alpha map Vn to Vn plus 2 and x minus alpha will bring it back to Vn, right? Okay, so proof, let's do this for L equal to 1 and then L general case will follow immediately. So let V belong to Vn. So we are going to do some computations today. Okay, so this is the just to get the data correct. Then x alpha, x minus alpha. So I'm going to compute this for the first one for L equal to 1. Okay, so I need to get x alpha, x minus alpha acting on V. Okay, so that is what we're doing, plus, well, x minus alpha, x alpha acting on V. Well, why do I write it? Because I have a expression in the Casimir which is x alpha, x minus alpha and x minus alpha, x alpha, right? So that is simply half omega minus x bar square acting on Vn, right? But I know omega acts like q and x bar acts like multiplication by n, right? So this is simply half q minus n square times Vn. Fine? So I have not done anything non-trivial. So, yeah, okay. But I want to compute this guy, right? So, x alpha, x minus alpha, minus x minus alpha, x alpha, acting on Vn. I can compute that because that is a bracket, right? That's the bracket of x alpha and x minus alpha. So this is x alpha, x minus alpha, acting on V in bracket, and the bracket is x bar, right? So x bar V is NV, right? Because V comes from VA. Okay, so let's keep that upstairs there. And divide by 2, I have one expression, right? So add get. So I add them and divide by 2. So I'll have x alpha, x minus alpha acting on B. X alpha, x minus alpha acting on B would be I add and divide by 2. So I'll have a half q minus n square plus n and divided by 2. So I'll just write down what it is. So 1 by 4 q minus n square plus n, sorry, 1 by 2 acting on B, right? Right? 1 has q minus n half q minus n square plus n, right? So this, if you rewrite, you will get that 1 by 4 q minus n minus 2 into n B. And that's precisely the proposition for L equal to 1. Okay, so this gives proposition for L equal to 1. Okay, so we have done one computation, and now everything follows because of the properties of x alpha and x minus alpha, which we have already written there, that it takes Vn to Vn plus 2 and the other one takes Vn to Vn minus 2. So if I want a general formula, I just use whatever we have just done along with that property, right? So now if I take P in Vn, then x minus alpha L minus 1 V will be in Vn minus 2L minus 1, right? So each time I will be decreasing by 2, right? So if I apply it L minus 1 time, I am going to decrease it by 2 into L minus 1 times. So now to compute that x alpha, x minus alpha to the L, so I just write it as, so x alpha, x minus alpha to the L acting on V can be written as x alpha, x minus alpha to the x minus alpha to the L minus 1V, right? But this guy comes from Vn minus 2 into L minus 1 and apply the previous right? So if V comes from Vn, this is what I will get. But now V is coming from L minus 2 L minus 1, you will get exactly what you want. So this would be equal to 1 by 4 q minus n minus 12 into n minus 12 plus 2 times. And so that proves the proposition. So this is a very simple computation. But this already tells us a lot of things. So similarly, the other cases, so I will not do that. So what are the corollaries? Now we can say various things about the k types that will appear. Corollary: if I take a non-zero vector in VA for some n, I can look at these propositions and write down the k finite vectors, right? So then V sub k is, well, the span of the vector E. Then you keep applying these x alphas and similarly x minus alphas, take the span, right? So that is your whole thing. So this is direct sum L greater than equal to 1, x alpha V, x sum L equal to 1. So there is a sum here, x minus alpha to the right. So this is your Vk. Well, why is that? So I form the space, right? So I take a V, which is in Vn, and I keep applying x alpha. So remember the x alpha increases, right, the weight. Vn goes to Vn plus 1, Vn plus 2. So if this is in Vn, this is going to be in Vn plus 2l. And similarly, this is going to be on the other direction, Vn minus 12. So if I look at the space, it is invariant under h bar, right? Because each of these are eigenvalues for eigenvectors for h bar. It's invariant under x alpha. Why is it invariant under x alpha? Well, this part is obviously invariant under x alpha. This, if I apply x alpha to it, I can use the proposition. That tells me where it lands. It goes to it goes one step behind, but it's already there, right? And similarly for x minus alpha. So this space we have formed is invariant under x bar, x alpha, and x minus alpha, and that spans the Lie algebra, right? So it is invariant under the Lie algebra action, so it will be invariant under the universal analytic algebra. Okay, so because RHS is invariant under x bar, x alpha, and x minus alpha, and so with respect to all of UGC. Right? So that because of the reducibility, it has to be your V sub k. There is nothing. Okay. So now, well, that is how our Vk will look like. So let's see. I'll keep this. We may need it later. Okay, so I'll try to stop around 11:45. So we have some time.
Here, when you are looking at the speed,
so
all the other speed coming, they would be coming in. So if this was in Vn, then that would be Vn plus 2Vn plus 4Vn plus 6.
Yeah.
N minus 2, N minus 4, N minus 6.
Yeah.
So what about N plus 1, N plus 3, N plus 4?
So that can't count. So it has to jump by 2. So that's going to be the next. And of course, this, I'm not saying all of them are non-zero. It may be 0 at some point of time and then nothing will be there afterwards. Yeah, so those Vn. So this simply says that. So let's look at the nice case. Let's say this is 0, and then you jump by 2. You will have V2, V4, V6, and so on. Here you will have V minus 2, V minus 4, V minus 6, and all that. Let's say we have all of them. So we have all of them, but the odd ones will not be there. So the restriction will have only the even numbers. Okay. So those are going to be the conclusions, right? So let's see. Given pi define j pi to be all those n such that dimension of Vn equal to 1. Right? So it's either 1 or 0. So I am simply counting all of them which exist in the decomposition. So whatever you were saying just now tells us that. So which one should I keep? Yeah, I'll keep those. So because the weights jump by 2, the j pi has certain properties, right? So it consists of integers of same parity, right? So if you have 0, you will have 2, you will have minus 2, and so on. All or at least one-sided even ones or odd ones, right? So proposition. So this is easy now to conclude from whatever we have done. J pi. So if I take a pi unit, so pi is unitary reducible. So given pi, unitary reducible. J pi consists of integers of same parity, so it's either even or odd. 2, J pi is an unbroken chain, so you can't have some gap. Okay, you keep adding 2 or keep subtracting 2. If it breaks, it stops there. Okay, that's not difficult to see. 3, again because of the proposition and the q value and all that. Suppose I know that some Vn exists, some Vn is not 0, then Vn minus 2 equal to 0. So that means it ends there if and only if. So J pi consists of integers of same parity, so it's either even or odd. And I'm saying it cannot have gaps. So I can have 0, 2, 4, 6, and then it starts from 22, 24. That can't happen. There is no gap. It's an unbroken chain. Huh?
Yeah.
Suppose Vn is not 0, then Vn minus 2 is 0 if and only q equal to n into n minus 2. And Vn plus 2 is 0 if and only if q value is n into n plus 2. Here it is n minus 2 and plus 2. Okay, so that's not very important. I mean, these things when you read that will come up. So let's look at this thing. So that already tells us how the k types are, right? It gives a lot of information on k types. J pi consists of integers of same parity, right? That follows from whatever we have already written down there. Because x alpha will go from Vn to Vn plus 2. So if Vn is there and x alpha V is non-zero, then I have Vn plus 2. And then I will have Vn plus 4 as well. Similarly, the other way. And if I put together all of them, that is already V3, right? That is what that corollary means. And because of irreducibility, this is the thing. There is nothing else. Okay. So J pi has to have integers of same parity. If there is one even, everything else is even. If there is an odd number, then everything else is odd. It's an unbroken chain. Well, so think of J pi as a sequence of number, and if it breaks at some point, and let's say it starts after some time, you take whatever is there at that particular point, that is invariant under the Lie algebra action, just like what we have done. But it's irreducible, so it has to be the whole thing. So whatever is coming after a gap cannot come, right? And this is also easy. So let's prove the third one, because that is its computation. So if Vn is non-zero and Vn minus 2 is 0, so you apply the proposition with L equal to 1, right? So let's take V in Vn and look at x alpha, x minus alpha V. Well, this has to be 0, right? Because x minus alpha V is going to be n minus 2. And Vn minus 2, I want to look at when it is 0, right? So this is simply q 1 by 4 q minus okay, so let's write down this. It should be, what do I want to answer? So I know what I should write this. So then Vn minus 2 V. Right? So Vn minus 2 will be 0 only if that particular eigenvalue is 0. Right? So if the eigenvalue is non-zero, then I have a non-zero vector here. So x minus alpha V cannot be 0, which means Vn minus 2 cannot be 0. Fine? So Q has to be equal to n minus 2. Use the other one to prove the Vn plus 2 is 0 can only Q 0. Okay?
But if Vn is non-zero, how are you saying Vn plus 1 is 0?
Because it doesn't exist in the decomposition for V sub k, the k finite vectors. Because we apply x alpha will take Vn to Vn plus 2, and x minus alpha takes Vn to Vn minus 2. right? So I start with any non-zero vector in Vn. So let's say one Vn which appears, right? That's a dimension 1 space. You take a non-zero vector and then form the space, right? So this space is invariant under the Lie algebra action because it's invariant under x bar, x alpha, and x minus. So it has to be the whole space V sub k because of irreducibility. So that tells me that you can't have integers of different type. Fine. Okay. Okay, so now I can probably write down what I want to say, which is the classification in some sense. Yeah. This is the classification. So let's say phi v is unitary, irreducible. So we have already proved that J pi can be, J pi will have only integers of same parity and it's an unbroken chain. So, well, what are the possibilities of J pi? So, suppose J pi is even time. So, what do I mean by that? It has only even numbers, okay? Or odd time, right? These are the possibilities. So, or odd time. If q is not equal to n into n minus 2 for any positive even integer n, okay, so if q is not so, because we are trying to rule out the case where some of the vn's can be 0. So if q is not equal to n and n minus 2 for any even positive integer n, then J pi is doubly infinite. Right? That means it consists of all even numbers or all odd numbers. Okay, so these are the cases for principal series, both principal series and commutator. So that is one case. B. So again, J pi is even type or odd type. If so, we ruled out the case or we have analyzed the case where q is not equal to n into n minus 2, then you have J pi going in both direction. If the value is n into n minus 2, for some positive even integer and even or odd, right? So odd type meaning you look at odd integer. And so don't worry about the positive integer, because if n is negative, you write it as minus m, you will have minus m minus 2, that is m plus 2 into m, which is again of the same form. So that's why it's written like this. Then there are three possibilities. One, J pi n plus 2. So remember, n is positive, so n goes from n plus 2, n plus 4, and so on. 2, J pi goes from minus n minus 2, minus n minus 4, etc. stops there. And 3, well, these are the finite dimensional representations, so they are not unitary, so we don't count them, but they are admissible. Minus n plus 2 all the way to n minus 2. Okay. Yeah. Yeah, so you will have only negative ones.
Yeah.
You can't start at 10 and 8, 6 and go on. You have to start at minus 10.
Yeah.
So n is positive.
But you have
Yeah, that is enough. That takes care of all the cases. But this is more important. This cannot happen that it starts at a positive number and then go all the way to the negative.
why that is enough?
We'll see. That's not a very difficult. Okay, so these are the possibilities. Again, these things are easy to prove just by looking at the properties of X alpha, S alpha, J pi, and so on. So this is the holomorphic discrete series. Holomorphic discrete series. This is the complex conjugate of that. That is the anti-holomorphic discrete series. These are finite dimensional representations, which we don't because they are not unitary. Okay? But when you analyze the admissible representations, of course they come. Okay, so let's take some more time and finish off this. So proof of this is simple because now we have all the tools we need. So let's assume J pi is even type. What type is done the same way? Assume J pi is even type. So let's take A. So Q not equal to n into n minus 2 for any positive even integer n implies Q is not equal to n into n minus 2 for any even integer. Right? That is why it's enough to look at the positive. Because if n is minus m, then it's minus m into minus 2, that is m plus 2 into m, which is on the same form. So if q is not equal to that, then of course j pi has to be the right? So this implies that that's what we have already written down, right? So that is gone. Vn is 0. Yeah, so Vn is 0 finally, then into q is n into n minus 2 and things like that. So this tells me that Vn is not 0 for any n in j pi. Sorry, is not, let's say, n appearing in V sub kd position, and so it will be doubly infinite, right? So that implies j pi is doubly So let's see the second case, just to make sure that we understand this. So we go, so n is positive, so we go from a positive number and then to the right, that is one possibility. Or you take the negative of that n and go to the left, right, all the way to the negative. And again, these are all unbroken chains and so on. So let j pi be even and q equal to n into n minus 2 for some positive even integer n. Now how do I know which direction I should go? So I look at some element in j pi. Okay, so let j belong to j pi and j greater than or equal to n. Okay, so well, j could be less than or equal to n, so that's the other case. So let's look at j greater than or equal to n. So I have n and j on the right. So and that j belongs to j pi. That means that particular k type appears. So I want to say all the ones from to the right of n will appear. Right? That's what happens.
You are taking positive, and you said that you will take care of it.
Yeah. Because if I change n to minus m, you have minus m minus 2. So that is m plus 2 into m, which is again of the same form. I want to say it is one-sided, right? If q is equal to n into n minus 2 for some positive even integer n, I want to say the j pi, the k types that are appearing are one-sided. So let's take one j from j pi. Assume that j is greater than or equal to n. That means I want to say I go to the right, right? So I have n, n plus 2, n plus 4, and at some point j, and then go on. Okay? And I want to say that is j pi. Okay. Okay. So then, for any n greater than or equal to j, right? So I think it's better to draw these pictures. So I have m here, I have j here, and for any m greater than j, v m plus 2 cannot be 0. Cannot be 0 because v m plus 2 is 0 if and only if q is of the form m into m plus 2, right? Because q is not equal to m into m plus 2. Because m is greater than j and q is n into n minus 2. N is much smaller, right? So it cannot happen. So you will have all the VMs coming from j onwards, right? So from here onwards, everything will be there. So I want to say everything in between is also there, right? So again, because of the same reason, so okay, I'll keep that and then about this. And these reasons are the same. Okay, you just have to analyze what are the possibilities. There is nothing too difficult involved here. Okay, so let's try to complete this. For n less than to m less than to c j, so now m comes here. V m minus 2 is not equal to 0 until q equal to m into m minus 2, right? That is when because of that proposition implies j pi will have to be equal to n. No, I need to say Vn minus 2 is 0, right? So where am I? Q cannot be equal to yeah, okay. So when m is in between, Vn minus 2 can be 0 only when q equal to m into m minus 2. And that will happen only when m becomes n. Right? That is when m equal to n. Right? That is q equal to n into n minus 2. Then that means v n minus 2 is 0. Right? So from here onwards it's clear. In between it can be 0 only when q becomes n into n minus 2. That means v n minus 2 is 0. But once the chain is broken, it has to stop there. So this is the only possibility. Okay. So I'll leave the other cases to you. Okay, so here there is something to, okay, maybe I can do that because that is important. Why it is only from here? Well, it's the same argument. So anyway, I'll time is over. So I'll stop. Similarly, if j is, so you do the same thing. Okay, so we have done only one case, right? So we have assumed that j is greater than or equal to. So if j is less than or equal to minus n, then you argue exactly like the same way. If I take anything less than this, the product cannot be q, and so all those things will be non-zero, and between m and minus n, again this cannot be 0 until q value becomes something, and once it becomes that, the next one is 0 because of that proposition, and so from there. Okay. So similarly, j is, this would be minus n minus 2, minus n minus 4, etc. Okay. And similarly, the other case, so the next possibility is that there is a finite chain like this, and the q value becomes exactly what you want, only in this place and this place, in between it cannot. So this takes care of the what is known as the infinitesimal classification, but we haven't finished saying these are all the unitary reducible representation, right? So I'm going to make some statements and I'll stop in a minute. We'll do that in a little bit of detail in the next. So we have a list, right? The list allows you to compute the k times and the q value for the list. Okay. Now I take an arbitrary unitary reducible representation. I look at the q value. Well, so I have to say that the q value will have some condition. Okay, we'll do that in the next class. So let's say q less than 0 is a condition. If in the first case, so let's say j pi is even type. So I have 0, 2, 4, etc. and minus 2, minus 4, etc. That is one case. And we show that q is less than 0 there. Okay, so depending on the parameter, I say q may be less than minus 1/4 or something like that. Doesn't really matter. Some condition on q you will get. Okay. Then you go to the list. For all q less than 0, there are these representations. So if j pi is doubly infinite, containing all even ones, and q is, let's say, minus 3, there is a principal series representation which gives you exactly that. So the infinitesimal data for that particular principal series representation matches with the one we have started with. Okay? Then they have to be unitarily equal. So that is the theorem I'll state down. So that tells me the list is the list. So that finishes everything. Okay, so I'll try to write down a few more lines in the next class. And then we'll see if there is enough time. I'll say something about the Bangalore.